Great. Well, welcome. Thanks very much for the invitation here to present this last tutorial, I guess. So I'll just sort of continue where Ankit stopped in his previous talk. And first I want to, I guess we want to talk about three things today. One is sort of, continuous investigation of convexity. So that's going to just, sort of trying to fill in sort of the announcement of Ankit that I would sort of talk a bit more about the non-abelian case, the non-commutative case. And the interesting, again, why these convexity properties are going to be interesting is because they underlie these optimization algorithms in a way that we're just, now understanding in this framework. Then I want to change gears a little bit and talk about a sort of very natural class of marginal or scaling problems, sort of generalizing what we've seen so far. I'll talk mostly about examples, so the case of the abelian case, which is basically about probability distributions, and the non-abelian case, which is relevant for quantum states and quantum marginals. So I'll explain what this means and how it is related to this moment map that we see in the previous talk. And lastly, I want to discuss how in great generality, answers to these problems are given by convex polytopes called moment polytopes. And sort of that they have, just like in this theorem of Kempf-Ness that Ankit described, there's sort of an optimization and an invariant theory characterization that generalizes this null cone perspective that we saw previously. Okay, so that's the plan. We'll see how it goes. So let's just start simple. So here's, let's talk a bit about invertible matrices. And I guess we saw these a bunch of times, right? So Ankit took the gradient at the identity element. So somehow we have to know what's the tangent space of a bunch of invertible matrices, of the space for invertible matrices. And basically the idea is that any invertible matrix, right, we can write as an exponential of a matrix. So mat n is just complex n by n matrices for me. And so because the exponential then we can sort of Taylor expand in first order, right? So the identity plus s times a plus something small. So we can really think of A as the tangent space. Okay, and so of course the general invertible matrices are some proper manifold, but that's a way sort of to think about the tangent space at the identity. So here's a little picture. That's the identity element in the group. That's some other group element. And so A specifies a path connecting these two things. Okay, and that's the sort of geometry that's going to underlie our group, and that's going to be related to these convexity properties. Maybe just two examples, right? So now we have this tangent space. We can restrict it. For example, if we restrict it to Hermitian matrices, that's kind of like R, then we'll get something positive definite. So it's like saying the exponential of a real number is positive. If it's purely imaginary, that is, if it's of the form I times k for Hermitian k, then we get a unitary matrix. So there's this interplay, right? So restricting the tangent space gives us different directions. One is sort of compact, the unitary one sort of changes the norm. We can also sort of combine these two things, and that's going to be important in a bit. So any invertible matrix we can write as a polar decomposition. So we can write as a product of something unitary. It's like the phase, right? Plus the times the absolute value, which is this positive definite thing. So that's that. Okay. So now here's the reminder. Sort of maybe, well, I guess the way my slides look is quite different. The notation should be roughly what Ankit used. So recall our setup. We have an arbitrary representation for simplicity of GLN. It's represented on a vector space V. And the kind of compatibility that we demand, and that was always true previously, was that the unitary subgroup is going to be mapped into the unitary subgroup of this vector space. So this vector space is actually a vector space with an inner product. And what we're saying is that unitary matrices, they act in a way that preserves the norm of vectors. Okay, so that was the reason why we ignored those in the last talk. Now, the object that we considered, that Ankit considered, was given a vector. We look at the squared norm function. And we think of it as a function of the group element. So to given a group element, we study we study this norm squared. And then the moment map was just a gradient. So here I tried to write down a sort of a more explicit definition. So it's a function, and I put gradient in quotes because we're really interested in these directions that have the potential to change the norm, or that sort of, we ignore the directions that will not change the norm in the sense that we only plug in these Hermitian matrices, right? Because we know that e to the IH was unitary, so those will not change the norm. So we do only Hermitian matrices. So what we do is we take a Hermitian matrix, we look at e to the HS, we look at what it does in the representation to this vector V and how the norm squared changes. Okay, and so the change in first order is this object. I add this factor 1/2 for no good reason. And so we can assemble all these derivatives into a joint object, into a single matrix, and that is just a gradient. Okay. And so more precisely, the moment map is something that takes a vector, it sends it to a Hermitian matrix, in this case, a single Hermitian matrix, such that any component of this matrix, that is, trace of this moment map of V times H is given by the norm, change of the norm squared in that direction. So that's the geometry underlying this business, and we saw it in the last talk, and saw several examples. In particular, we saw this statement, and that was sort of one of the main results, this Kempf-Nest result that Ankit spoke about. And the claim was that for any vector in the representation, the following two things are equivalent. This vector is not in a null cone, so it means that if you apply arbitrary group elements, you take the closure, you cannot get 0, if and only if there exists a scaling, so you can transform your original vector V into another vector W, possibly by taking limits, and such that this vector is non-zero, but it is mapped to 0 by the moment map. That is, the gradient vanishes. And so again, left-hand side was this null cone. The right-hand side, Ankit discussed in 3 examples, I think, is a kind of a generalized notion of double stochasticity. So one can set up things in, one can set up a representation, a group for matrix scaling, such that this corresponds to double stochastic proper. One can do this the operator scaling version, where it's completely trace preserving in unital. And one can do a tensor scaling setup, right, where it's really sort of these locally maximally mixed marginals, okay? And I'll recall these things. But somehow that's the situation that we have. And so I'll not quite prove this result, but I want to sort of give you an intuition why something like this should be true. And so really what I want to show to you is why, if the gradient is 0, this implies that we're actually at a minimum, at a global minimum, at least on the orbit, okay? So what I want to discuss is the following result. I want to say that, well, suppose we are at a vector W in the representation, and whatever we do in the, whatever point we go to in the orbit, we never get something of a smaller norm. Then I want to discuss, why is this equivalent to saying that the gradient vanishes at that point? And so, sort of infinitesimal, it's clear in one direction, right? If we're at a minimum, then the gradient must vanish. So that's kind of this situation. But somehow, why should the converse be true? And, Ankit said, well, convexity. So let's try to see what this convexity means. Also, you should sort of interrupt me at any point. And if I don't see you, just shout. So what is this kind of convexity, right? So basically, we want to show that this picture makes sense, and it's sort of even we can extend it to a global picture. Whenever locally the derivative is 0, we are at a global minimum. And so what we're going to do is the following. So let's just track the evolution of this norm. So let's take an arbitrary group element like so. So we want to prove that if the gradient is 0, then this holds, right? So let's take an arbitrary group element. Let's take this polar decomposition from before. So you write it as a unitary times something positive definite. And now, sort of the only thing that we're going to do is we're going to show that this function is a convex function. So what is this function? So it has a real parameter, f of s. What we're doing is we're just applying, the group action, the representation of u times e to the hs to this vector w, and we're computing the norm squared. Now, for s equals 0, this is just our original vector, w, and so the norm square of our original vector. For s equals 1, well, we're just applying u times e to the h, so we get g, so f of 1 is sort of the left-hand side of this inequality. And so the only thing we really want to argue, well, is if this thing were convex, right, then somehow the implication from the right-hand side to the left-hand side would be correct, right, because somehow the moment map was exactly the derivative of this norm squared function at s equals 0. Okay, that was exactly our moment map from before. So somehow we get that, well, f prime of 0 is 0 if we assume that the gradient is 0. If the moment map is 0, it's going to be true for all h, okay? And hence we get this inequality. So the important thing that we have to argue is why should this function be convex. So right now it's a one-dimensional problem. We have a path, a certain path. It turns out it's a geodesic in this group GLN. So we have a geodesic in this group GLN, and we want to show that the squared norm function is going to be convex along this direction. Okay. So that is this.
What is the parameterization of the path?
Did I write T? Could you say this again? Sorry. I'm sorry. I guess T should be 1 here. That is a typo. Yeah, I'm sorry. Yeah, so it should be f of t large equals to f of 0. Right? This sort of convexity. Somewhere, any point lies above the tangent at any other point. Sorry about that. That should be 1, and so that this should not be there. So that would be true for any t, and then in particular for t equals 1, we get our claim for the specific group element G. Thank you. So that's so why should this be true? So well, let's prove convexity. So what we do is we take 2 derivatives. We show we get something non-negative. And so that's going to be the only calculation in this talk, but I think it's kind of illuminating to sort of demystify this geodesic convexity business. So that's the function we care about, right? So we have our starting vector W. we apply this group action. We apply the action of this group element u times e to the hs. H, remember, is Hermitian, u is unitary. Now, because u is unitary, we can just forget about the u. It doesn't change the norm, and this was this compatibility condition that unitary matrices act by unitary transformations on the representation space. So now we have this guy over here, and now the second thing to observe is that if we have a path like e to the hs in the Lie group, by the representation is going to map it to another path of the form what I call e to the h tilde of s. Now h tilde is again Hermitian, but it's Hermitian in the Hermitian operator on the representation space on V. Okay, so basically I'm saying that this exponential map commutes with a group action in a way. Okay, that's so if you like Lie groups in the algebra, some kind of this h tilde would be the Lie algebra representation, but that's not so important. Essentially, this h tilde is kind of the derivative of the action at s equals 0. But okay. So now, if we have this pleasant form, we can just calculate, okay? So f of s now is the norm squared of this object, so we can just write it using this inner product like so, okay? Now we take one derivative, well, we have taken the derivative here and there, so we basically get this guy, so we get an h tilde down here. We take another derivative, well, we get h squared, right? And I guess we get everything twice from the left and from the right, so this is 2, that's a 4. But this thing is just an L2, is just a norm squared of a vector, namely it's just a norm squared of the vector h tilde e to the h tilde of s. And so this thing, because I guess there's a square missing, sorry, that's a square, this thing is non-negative, okay? And that's exactly the convexity. So that was everything that's going on. Okay, now so I'm using that h tilde as Hermitian here. That's what's going on. And one can do a similar calculation that shows that even the logarithm of this norm square is convex. Are there any questions about this? Okay, so that's like bilinear function. We're kind of taking derivatives. That's sort of pleasant. Maybe I just want to say to conceptualize a little bit what's going on. Maybe this will not be completely meaningful. One can there's a formal analogy that one can make precise between what's going on here when we take these derivatives and what's going on when one looks at what's called the moment generating function, right? The moment generating function of a random variable x is the expectation value of e to the sx. So when you take derivatives and you look at 0, you get all the moments, sort of one by one. And so that's really what's happening, right? That's why when we take these derivatives, we get, we have identity, h tilde squared. Next thing would be h tilde cube, and so on and so forth. Yes?
So your h tilde is Hermitian?
That's correct.
So essentially, you don't need even to differentiate, so your function is a positive combination of exponents.
That's right. You could do it in eigenbasis, right?
This is why log convexity.
That's also correct, yes. That's maybe
it's actually kind of a universal barrier.
Excuse me?
It's also how they construct universal barriers in interior polynomials.
Very good. Yeah. Well. Great. So that would be a maybe an even easier proof in a way, right? I wouldn't have to even, well, I like deriving, taking derivatives of matrix valued exponentials, but you may not. So that's a great way of not doing it. I agree.
The point is that I was kind of mystical to it. The point is that this is how people solve scaling problems.
Yeah, no, I understand. Yes, I agree. Yes. Yes. Let me just say, if you like this idea of a moment generating function, then the logarithm also has a nice story associated. I guess it corresponds to a cumulant generating function. And the first couple cumulants are the same as the first couple centered moments. So again, you get all the same structure here, right? Some other, the centered second moment is non-negative, hence also log f of s is geodesic convex. Or, I mean, what you said before is, of course, just as good of an explanation. What I like about that calculation is sort of it shows something that's going to pop up in Thursday's talk, right? Some of the second order robustness requirement. It just sort of popping up because you get another h here, and then you can just do Cauchy-Schwarz inequality, basically just get such kind of results. So you can, not only is it a convex function, but you can control the error that you make. You control the third derivative in terms of the second derivative, which is going to be useful in Thursday, sort of. That's why I guess why I wanted to display this here in this general context. Okay.
For the last inequality, one needs to say S is say in 1 or something. I mean, if C becomes very big,
Yes.
Order derivatives bounded by constant second order?
Yeah. There's some norm one stuff in the background that we'll not worry about. Yeah, of course. I mean, somewhat, yes. It's also that this interpretation that I spoke about here only makes sense if things are unit vectors. So that is of course correct. But somehow the conceptual point is this, right? Somehow you just get the moments, and then somehow, things are sort of just simple inequalities of inner products and operator norms. So this function C is essentially, I mean, up to S is basically the operator norm of this H tilde. So it's sort of very, very pleasant. Excellent. So that's that. So somehow that's the convexity, okay? And so now coming back, that tells us why local minima or local extreme points are global minima of this norm square function. We could also ask a slightly more complicated question that I sort of promised to mention because it's again going to show up on Thursday, which is the question, what are actually the vectors where the norms is the same, right? So now we know that we have a minimum, but it's probably degenerate. How degenerate is it going to be? Well, we have a candidate. We know when we apply a unitary matrix, then the norm is not going to change. Is that the only case? And the answer is yes. And sort of in the way one can sort of see it easily, I guess it's not so easy because there's two slides that you need to combine in your head. So when do we have such equality? Well, remember G was u times e to the h. Okay, so let's keep this in our minds a little bit. So when do we have f of 1 equals f of 0? That was our little function, right, that tracked the norm. Well, it's certainly necessary that the second derivative of 0 is 0, because otherwise, even infinitesimally, the norm would increase. So we have this. But now the second derivative, right, was basically, it was just applying this Hermitian operator h tilde to e to the hs tilde times w. But if s is 0, this exponential goes away. So really what we are saying is that when we apply this infinitesimal action, this h tilde to w, we just get a 0 vector. It's the norm square 0. One sec. Yeah. Yes, sir.
Do you need to scale it with derivatives? Like to take power 1/3 or 1/7?
So here's a square. That was what I said.
The last line.
There should be something about S. S should be in there. Yeah. What Peter said before. Yeah. The S should be in there. Yes. So let's come back here. So somehow the conclusion that we get is that this h tilde operator doesn't do anything. It annihilates our state w. And this means that the exponential of it, right, is just going to preserve the vector. Right? Because all the, if you think of the exponential as a power series, everything but the identity term will just annihilate our vector. And so it means that, sort of when we apply the action of this group element G, really we are only applying the unitary. And so we see this equivalence, right? So the minimal points in this orbit, in this GL orbit, are going to be simply a unitary orbit. So those are the minima. And so then one can work a little bit more and look at the orbit closure, which is a situation that Ankit spoke about. And the conclusion, which is the theorem of Kempf-Ness, is that in each GLN orbit closure, the vectors of minimal norm, they form a single UN orbit. And moreover, the GL orbit to those is actually a closed orbit. So the situation roughly looks like so, right? We have some orbit closure here. So I only spoke about orbits, but we can also speak about closures. Now in this orbit closure, there is some point of minimal norm. Say it's non-zero, it's this W here. And then this point comes with its own unitary orbit. So that's the geometry that's going on. And that's kind of why we ignore this unitary directions. We only like Hermitian matrices for the purpose of these talks. Because some of the unitaries don't do anything. And in a sense, it's the only thing that we don't have to worry about. Now, this has algorithmic implications. We'll see this much more clearly in the next talk. And the idea is basically because in such a way, one can reduce orbit closure intersection problems, like Avi mentioned his talk, I think, Harm mentioned, Ankit mentioned, such as the following, right? So you have two vectors, VV prime. You want to know if their orbit closures intersect. You can reduce this now in essence. Well, if you could make this into an effective method, you could reduce this to an orbit equality problem for the smaller compact group U, right? Which is sort of you would think is a more well-behaved problem. And so that, I think we will see in great detail on Thursday how this plays out in the context of operator scaling, say. Okay. Good. So here, this is a summary slide. So somehow the point, I guess, is, right, we have this convexity property, and it should really ensure that somehow gradient methods, in principle, right, sort of, even if you don't think algorithmically just as a flow, it will converge to some extreme points, and those extreme points will be minima, but what we discussed about, right? So somehow we'll sort of, it suggests that, one can build algorithmic solutions based on gradient methods that exploit this property. And here's and so somehow by this duality, we'll at the same time converge to a global minimizer of this norm square, as well as the dual problem. And if, but we saw in the duality that if the left-hand side is larger than 0, the dual optimum will just be 0, right? And so here's a little picture of how this plays out. So I should say somehow, I think in a way, this is sort of goes back to Kirwan. So Francis Kirwan studied this gradient flow, actually to prove statements about the cohomology of certain symplectic quotients, and it's sort of beautiful that sort of now we have this completely different scenario where we can solve all the scaling problems using such ideas. This polytope is not yet clear what it's supposed to mean. It will pop up later, but you see a little, well, you faintly see a little red curve here. That would be an example of what happens when you apply this gradient flow. So we sort of, with Matthias and collaborators, we sort of non-algorithmically sort of discussed this. So we just did the gradient flows on a computer, and so we sort of, in a context that's going to be related to quantum entanglement, and we'll talk about this later. But the point is like this picture is in the space where the moment map maps you to, and something is flowing to 0, which is exactly the stochasticity condition that Ankit spoke about. So I hope that this picture is going to be more clear at the end of my talk. Excellent. So just to continue what I was saying before, so somehow I guess this convexity is really what underpins, certainly gradient methods, and it's sort of natural to look at continuous methods. So this we will see on Thursday, but also I guess as Leonid was saying before, you can think of these discrete algorithms somehow as large step versions of this. I'm not sure how I guess it's certainly true that the infinitesimal version of the large step algorithms are gradient flows. The other way around, right? It's sort of this maybe different between going in all directions at the same time and looking only at the coordinates. So, sort of, but I think certainly on an intuitive level, that is what's going on. And I guess that this connection, right, going from these discrete scaling algorithms to continuous one is what inspired these recent works, right? More so than perhaps the Kirwan's gradient flow from the 80s. So that's very interesting. Avi already mentioned that, in order to make, say, even these discrete algorithms work, you need some bounds, some a priori bounds, and how large, how small can these quantities get? And that's somehow amazingly, this is provided by invariant theory. And that maybe, I think, in Raphael's talk will appear to some extent. Yeah, I'm also going to postpone some to-do items to the later talks. Great, so that's that. So any questions about the convexity part? And let's talk about marginal problems and moment polytopes. And let's start so we'll switch gears a little bit. We'll come back to this picture, this polytope that you saw before, which was a moment polytope. Yes?
Is there some convexity here to reduce to one variable?
Yes.
Something in many variables at once?
I think you can change the direction which you flow, but I think in the end, this geodesic convexity, as far as I know, is always along a single variable, like sort of a curve, a geodesic in the space of the group. No, I think at least in a naive way, it will probably, because the non-commutativity of the group somehow will probably not be right. Maybe someone wants to comment. Okay.
Actually, if you take a completely positive operator, plug in exponent, operator exponent, take determinant, take logarithm of that thing is not wrong. That thing is not wrong.
That's right.
Yes. The abstraction is actually very interesting. It's because exponent is not operator conjugate.
That's right, yeah. So that's the non-commutativity I was alluding to, right? Somehow, indeed.
We are dealing here with not operator convex, but geodesics is because this is
that's right, yeah. I mean, so as a consequence, right, if you only work with matrices that commute, everything would be happy again, right? That's kind of the torus case. So there, sort of this geodesic convexity lifts to a global property, but for non-commutative groups, somehow there's this obstruction, which makes everything more interesting here in a way. Yes. The nice thing is that, all these gradient flows, they stay in such a, they stay at least in a nice group orbit, and so one can use these techniques even along, right? So it's like one can sort of, in a sense, one only cares about such, curves in the space, so one can hope to reason about in this fashion. Yes. Great. Okay, so let's talk about marginals. So here's let's just forget everything we said about convexity and let's start simple. So here's a matrix, and I want to think of this matrix as a joint probability distribution. So let me start again. So we have a joint probability distribution of two random variables, p of x, y. A capital X and capital Y are the random variables. Little x, little y are the values that they can attain. Now I could arrange this thing into a matrix. So here's this matrix, and just think about what did we do for matrix scaling. So the thing that we cared about there, right? We cared about the row and the column sums. of some matrix non-negative entries. So that's exactly the situation here. And of course, the row and the column sums, they correspond precisely to the marginal distributions if I start with a joint probability distribution. Okay. So here these two marginal distributions are marginalizing over x is summing over the y's, which means summing over the columns for each row. And likewise, P of y, I would sum over the, I guess, the columns. Maybe I said this the wrong way around, right? So this is row sums, this is one marginal, that's the other marginal. Now you could ask, what's the inverse problem? Suppose I hand you two marginals, can you always patch them together to a global joint distribution? And here someone's very simple, right? You could just take, for example, the tensor product that would correspond to just taking them as independent random variables. Like their joint distribution just makes the two of them independent. So that's a simple question, but you could sort of make it more complicated by actually demanding that these marginals you would obtain from a scaling of some probability distributions that you start with, right? And so then this matrix scaling problem, right, what you could interpret as saying you start with some probability distribution. For example, if you want the marginals that are all uniform, right, the matrix scaling problem is exactly this. You start with some q of xy, some joint distribution if you wish, and then you apply this row and column multiplications, and you want to end up with some p of xy that has uniform marginals. But of course, this problem now makes sense for arbitrary marginals, not only for uniform ones, and we already discussed that. That's an interesting question one may ask. That's the setup that we care about. So we have, so what's a scaling of q, right? We just take this probability distribution q, we multiply it with some a of x and some b of y, we get a new distribution. If a and b are properly normalized, that's again going to be a probability distribution. You remember that the a's and the b's, they were non-negative. Some of this thing with like complex versus non-negative, right, there's a square function that was going in Ankit's talk. Everything sort of is like L1 versus L2. The idea is kind of you have a matrix that has L2 norm equals to 1, then the absolute value squares of each of the entries is going to be something that's a probability distribution. So that Ankit explained. So really what we care about is this object, so delta of qxy. And so let's unwrap this definition. So we take q of xy, we take a scaling. We also allow asymptotic scalings in the sense of taking limits. Let's say p of xy is such an asymptotic scaling, then we just compute the marginal distribution px and then marginal distribution py. And we ask what is that region, what is that object that we get, okay? And again, when I say here, I only want to look at joint probability distributions and normalize everything to total probability 1. So here, I guess, is an example. So this would be a joint probability distribution of two random variables. This probability that both are 1, they're never both equal to 0. I think it is properly normalized to probability 1. And the marginal distributions, well, they're like 3/4, 1/4 each in both variables, right? Some of the row sums 3/4, 1/4, the column sums likewise. So I could plot now a two-dimensional picture here where just the x-axis is the first of the two probabilities, the probability of outcome 1, and this is the probability of outcome 1 for the second random variable. And then 3/4 would be, say, this point. Now the scaling problem is basically about, suppose you apply scalings to this qxy. Suppose you left multiply, right multiply by these diagonal matrices with non-negative entries. You get another probability distribution pxy. What's the space of margins that you can get? And it turns out that somehow there's a nice answer. And basically what you do is you just have to look at the zero non-zero pattern of this matrix. So whenever you have a non-zero entry, you can think of the corresponding deterministic distribution, right? If it's sort of in the first row and the first column, like here, this would correspond to a distribution where x is always 1, y is always 1, and in the space of margins would be mapped to this green point, right? Similarly, I guess this would be mapped to that point, this would be mapped to that point. And somehow the only thing you have to do is to compute these points. You just look at the support of the distribution, the non-zero entries. You get basically a pair of deterministic distributions for each point in the support, and you just take the convex hull of the result. So that is the answer, okay? So you get this upper triangular that I guess is shaded here, but not there. So that's the situation. So here you can sort of see, I guess, why this is possible, right? If you apply these diagonal matrices, you could sort of try to push all the weight here, all the weight here, all the weight here, and sort of approach all these points. But somehow, I guess the only obvious thing, to me at least, is why one of the inclusions hold, right? Why is this thing always contained in a convex hull? Well, basically because somehow the map that takes a joint distribution to its margins is a linear map, right? So that's good. So if we have convex combinations upstairs, we get convex combination in the space of marginals. And also these scalings, they never increase the support of the distribution, right? If this q is 0 at some xy, then we can never make it non-zero. So the support is somehow good invariant object for our group action, and hence the answer, okay. And now we can make our life more complicated. We can ask more complicated marginal problems. For example, suppose we have two joint distributions of three random variables that overlap, like pxy, pyz. We could ask, when are they compatible? In this case, well, certainly necessary condition is that they have the same margin on y, where they overlap. Here it turns out to be also sufficient. Now you could ask me, okay, how about if we want to obtain this joint distribution as a scaling? I have no idea what a clean characterization of this is. Well, I'm sort of lying, but we'll see in a second what a characterization would be. But it's less obvious, right? And you could make your life more complicated. You could say maybe you also have given the marginal distribution of x and z. So it's like in this sort of on the cover page of this beautiful book, right? So here's some distribution, a three-dimensional probability distribution that two-dimensional marginals, right? They're these projections on these coordinate planes. And you're basically asking, given these three shadows, can I patch them together to a joint wooden figure or a joint three-partite probability distribution? So these seem like interesting problems, and the underlying structure is always that the solution to the general compatibility problem somehow amounts to a convex polytope. So the space of admissible margins are always convex polytopes, just because the marginal map is linear and the space of all probability distributions is a simplex, so it's a convex polytope. Also, the solution to the scaling problems here are convex polytope, but it's way less obvious, at least to me, why this should be the case. Okay. And the key fact that I want to sort of say is that really this is related to the fact that this map that takes a joint probability distribution to its marginals is essentially up to some squaring a moment map. Okay, and we saw this in this case in Ankit's talk, right? And so now let me maybe so now I'll tell you what's the general story for torus actions. Okay, for commuting actions, commuting group actions. So that's going to be a bit of a mouthful. Okay, so we have to look at the structure of a general representation. So let's go through this slowly. So we learned in Peter's talk and Ankit's talk that any representation of a torus, so T is the torus, C star tensor M, and on a vector space V, we can jointly diagonalize, right? Because all the operators commute. The joint diagonalization looks like so. Our vector space decomposed into a direct sum, and these direct sum are labeled by these weights that we saw, right? And the weights are basically exponents of the group variables, okay? And so we have some finite set omega that contains all these weights. And then we saw in Ankit's talk that the moment map is really just building combinations of these weights. So given a vector v in our representation that we write as a linear combination of elements v omega, v omega is a weight vector. That was the notation, the terminology that Peter used. So this is an eigenvector of the torus, a joint eigenvector of the torus. Then what this is going to be mapped to is just going to be mapped to a conic linear combination, a conic combination like so. It's just a sum over all weights times a prefactor, and prefactor is exactly the norm squared of the corresponding component of your vector. Okay. And so in particular, if V is a unit vector, an L2 unit vector, then this is a convex combination. And so there's a convexity that is already visible on the level of this moment map. Any point that's in the image for a unit vector is going to be a convex combination of these weights. Okay. So that's the general story. And so maybe this suggests why, in order to understand this image of the moment map, which we want to do to understand all the compatible marginals that we get, in order to understand the image, we want to not only take the moment map, but we actually want to normalize it by this norm squared, so that we do get a convex combination. It's just a way of making everything finite and compact, I guess.
So,
yes?
Can you view the first line, essentially the sum of squares times omega, is essentially as a polynomial with non-negative coefficients?
Yes.
Yeah. That's right, yeah. I mean, basically, the rest is just some general nonsense to have arbitrary torus representations. But really, the thing to have in mind is somehow, I guess a more. Yes, but note that in general, the space changes, right? So you could somehow think of this omega as something like a monomial. But in general, this left-hand side is like a generalized, it's like just how we can expand arbitrary polynomials into sum of monomials, we can expand an arbitrary vector and a general torus representation in a sum of, if you wish, generalized monomials, these weight vectors, v omega that we saw. So it's the same. It's a bit the same thing that went on in Ankit's talk. He had this, this n-dimensional torus acting on an m-dimensional space, as he explained before. And that's so there's a mismatch between spaces in a sense, right? This can be an arbitrarily large vector space. The space where we map to is only dictated by the group. So it's the same sense in that these joint distributions live in a larger space than the pairs of the marginal distributions. Okay.
But the case in which V itself is a space of polynomials.
I'll do this in a second, yeah, to come back sort of to more concrete grounds, yeah. I just want to display so briefly like what's the general scenario. The general scenario, this is a conic combination, that's a convex combination, and so we're basically interested in all these convex combinations that we can get. So clearly this object over here is just the convex hull of all the weights in our vector space. Okay. That's exactly the analogous to how the general compatibility problem is, or amounts, the set of all possible marginals, px, py, amounts to convex polytope. Now, the more sophisticated question is the scaling question. So suppose I start with some omega, some w, some vector w. I play arbitrary scaling, say I allow closure, so these are asymptotic scalings. I want this thing to still stay non-zero to make it interesting. And then I again look at this corresponding convex combination that I get. So the image under the moment map divided by the norm squared. Okay. So this gadget, this encodes the solution to our scaling problem. And that's sort of not obviously convex. It's not obviously clear what it looks like. What is clear is that somehow the only convex combinations we are going to get are somehow convex combinations of vectors omega that somehow on the support of our vector, right? If a monomial doesn't appear in the polynomial, it can't reappear by scaling. That's what I'm saying. And so that's somehow the answer. Okay, so this convexity theorem of Atiyah in this special case says that both of these gadgets are convex polytopes. This was obvious on the left-hand side, not on the right-hand side. On the left-hand side, you just get the convex hull of all the weights of our representation. On the right-hand side, we get the convex hull of the weights in this support of our representation. So support are exactly those weights omega, where the corresponding component is non-zero. So that's general story. Maybe we can appreciate and then go back to an example. Okay.
So
yeah.
his proof was using this machinery?
Yeah. I mean, in this general context, yeah. I mean, he proved a more general theorem, so like he didn't look at vector spaces only. Yeah, so he was looking not at points in vector space, but sort of more general symplectic manifolds. But that's you could also ask more refined questions about this. So maybe I don't do him justice if this is not the whole content of the theorem. But sort of that's maybe the content of interest for us. And indeed, like you could, I mean, if you think about how to prove this, right? I mean, so for example, once you knew it would be convex, it would be easy to go to all the marginals, like an LP thing. But yeah, I mean, it's not, one has to think about it a little bit, right?
But can I view it like this, that I have a polynomial, okay? I scale it, and I ask what is the gradient, what are possible gradients of vector 1, 1, 1.
Yes, I think that's right.
And it's, convex, it's a Newton polytope.
That's correct, so it's a Newton polytope. Hold your thought for 1 second. It is a Newton polytope. We'll get there in a second. Let me just make this general statement now to sort of summarize what we see beforehand, before going back. That somehow the point I want to make is that these concrete and interesting problems about probability distributions, they're classical marginal distributions, they fit into this more general framework, which is of sort of scaling problems and moment polytopes. So I guess I didn't say this strongly enough. These gadgets are called moment polytopes. They're instances of moment polytopes when the group action is abelian and where we know all the answers. Okay. And so so these marginal problems for classical probability distributions are a special case of moment polytopes for torus representations, and we can easily solve them in polynomial time if the vector is given to us in this nice form, right? If we basically know what the support is, it's sort of completely, it's simple, right? We just have to compute, we have to look at the support, the number of non-zero coefficients, which monomials appear, take the convex hull. So if someone gives you the polynomial as a sum of monomials, then this is an easy problem to solve, okay? But now, of course, you could ask, and I guess you did ask, what if the vector is only implicitly given? What if, this polynomial I don't write down as a sum of monomials? And then we also ask, how about non-commutative group actions? Okay, that's going to be even sort of, I don't know, an even richer class of objects to consider. Okay. So here, just very briefly, since we already mentioned this, okay, here's another example that is not a marginal problem in the sense of my motivation. So some homogeneous polynomial be expanded as a sum of monomials. So here these omegas have a very concrete meaning. It's just the exponents of the monomials that appear. And one can define this object called the Newton polytope, which I guess has a convex hull missing, which is the convex hull of all the exponents that appear of all the exponents of monomials that appear in our polynomial. Again, I'm sorry, there's a convex hull missing. So here's a simple polynomial, right? 5x1, x2, 3x1 to the cube, 7x2 to the cube, right? These are the three exponents that appear, and so we just take the convex hull of this object.
So there's a typo in the second line, therefore we should convex.
That's what I was just saying. That's correct. Yeah, that's correct. So same convex should be here. Yes. And so these Newton polytopes, they are moment polytopes. So if I gave you, right, if I gave you the polynomial as the sum of monomials, you could just, compute this convex hull using your favorite method. But it's an interesting question now that we can ask, what if you only have black box access to this polynomial? So you have some box and you can, feed it x's and you get p of x's. You could ask, can you still determine, membership in this Newton polytope? So then it's not obviously linear programming or anything like this. And then there's this beautiful scaling algorithms, I guess, for a class of hyperbolic polynomials that we may or may not hear about. And it's also for a certain point, right?
You can do not scaling. So you can do scaling.
Okay.
Scaling is not strongly polynomial.
Okay, good. Well, we'll.
Anyway,
Yes.
just to comment that membership in support is in Picard. So if you want to check whether given monomial is
That's correct. And so somehow that makes it all the more tragic that I forgot the convex hull here, right? So somehow, if I didn't have the convex hull, then this would be NP hard. Presumably, it might be simple, even beyond hyperbolic polynomials. What's your feeling? Very good. Good. So the natural question somehow that I'm going to ask is, is there a similar black box model in the more general case? Maybe that's something for the Friday discussion that one can ask.
It works possibly for surrounding local case.
I hope you will explain what this means. Good. So now let's slightly change gears and let's look at what could be a non-commutative analog of what we did, and that is related to quantum states instead of probability distributions, and quantum marginals instead of marginal distributions of joint probability distributions. So here's the setup, and now we are really talking about tensors and vectors, right? And it's clear why we didn't want positive, non-negativity anymore in the setup. So for simplicity, let's look at what we call a pure quantum state of a certain number of particles. Okay, so here we have d particles, d systems, and they're in a joint quantum state. When we as physicists say they are pure, what we mean is that they are described by a vector, by a unit vector that I call capital X, in a tensor product Hilbert space, where n1 is the number of degrees of freedom of the first particle, n2 of the second particle, and so on and so forth. Now, you may ask the question just like, so in a sense, this X is like a joint probability distribution of d quantum variables. And you could ask, what's the marginal distribution, say, of the first particle? And there's a mathematical object that describes this thing. We call it the reduced density matrix. It's given by an operation called the partial trace. Here we can write it down sort of in a language that's more analogous to what Ankit spoke about, and that's sort of more natural from this moment map perspective. We can define it as follows. So the quantum marginal, the reduced density matrix of the ith particle is an ni by ni matrix. It's actually a positive definite matrix. It's of trace 1 if X is a unit vector, and it's defined like so. Let's define it again by duality. For any other matrix A1, the trace between this hypothetical matrix, let me just make this red, the trace of the hypothetical matrix rho 1 of X is just given by this inner product, okay? You take the inner product between X and X after applying A1 tensor bunch of identities. So basically, this is an operation that only acts on the first particle, okay? And somehow you could think of this as the expectation value of the outcome of a measurement that you did on the first particle. What measurement you do or what observable you look at is parameterized by this matrix A1. So that's, in physics language, it's kind of saying like rho 1 captures all the local measurement outcomes, all the local information about your quantum state, about the first particle. In more concrete terms, we saw in Ankit's talk that rho 1 we can just write in a very simple way. If you flatten this tensor, so if you consider the tensor as a big matrix, complex matrix with n1, say, I guess, rows and n2 times nd columns, and we call this matrix M, then MM dagger, MM Hermitian conjugate is exactly a formula. So it's in some quadratic thing, it's sort of natural, and this formula makes it clear that it's positive semi-definite. In fact, as I was saying before, if X is a unit vector, then this thing also has trace 1. So we can remember that the eigenvalues of this thing form a probability distribution. So there's some there's probability distributions, 1 for each particle. But now the global thing is not a joint probability distribution, but it's a quantum state, and I want to consider, say, the case where it's a pure quantum state. You could similarly define this object, for other subsets of particles, not just a single particle, but say the first 2, the next 2, and so on. Maybe the first 5. So this definition makes sense for an arbitrary subset of particles. So now we could ask, again, a sort of a marginal problem. So let me state the general version of such a marginal problem. So we could ask, given a bunch of these operators rho, right, that may not come, well, given a bunch of operators rho s, on these tensor factors corresponding to systems S, we could ask, can we patch them together to a global quantum state? And we could ask that the state should be a pure state, so it would be given by tensor X, or we may ask that it is not, okay? So in other words, can we find, for example, a tensor X such that all these marginals, quantum marginals, are equal to these prescribed ones? So that's completely analogous to the classical problem we asked before. So here's a picture, right? Sort of I guess I could have drawn the same picture in the classical case. Bunch of particles, maybe you prescribe the marginals in these, of say the 3 particles here, of I guess the 5 particles there, and so on. Can I patch them together? Another example would be, maybe the state of individual electrons, well, of the average state of an electron, because we can't tell them apart. When can we patch them together to a global wave function? Okay, and that's a very fundamental problem about quantum states. One sec. And so in particular, right, so I just want to stress this, even though we're not going to follow up on it. If your tensor is supposed to be antisymmetric, then this would include, for example, the famous Pauli exclusion principle, which somehow says in pictorial terms that any 2 electrons can't be in the same state at the same time. So somehow one consequence of this is that the marginals, basically the average of a single the sort of what we call this margin of a single electron has a constraint. In this case, the eigenvalues can't be larger than 1 over the number of particles. Yes?
So in physics language, are you basically saying is there a pure state whose marginals are well defined?
It's like the inverse problem. So I hand you a bunch of marginals, and I ask can you actually patch them together? And from either by a pure state or even say by a general state. So we'll focus on the pure state case in a second. Let's just presume that we could even look at the general case, and we could ask this problem. And that's an interesting problem to us, because somehow many properties that we care about actually only depend on marginals of few particles, right? D is the number of particles. That's right, D is the number of particles. These n's were the dimensions, the number of degrees of freedom of the local particles, okay?
So you're looking for the pure state?
So let's not fix this ourselves. Here I wrote pure state. Let's for a moment actually, I wasn't super precise about this. Let's for a moment even worry, can we find a general state at all, right? Even in this case, right? I mean, so that, you could or you may not do this. If it's a general state, it amounts to an SDP, I guess, solving this problem, semi-definite program, so that comes in. Since we're interested in these moment maps, we'll look at a pure state case in a second. Let me just say why this is an interesting problem actually to study, right? More forcefully somehow. And the reason would be because these marginals, they tell you basically a lot of information about your quantum system. So typically things like energies, average magnetizations, all sort of observable quantities, they really only depend on a few particle marginals. And so somehow it would be very exciting if we could sort of characterize the sets of compatible marginals, because then we could, because somehow those only live in a very small space, right? In the limit of many particles, somehow this Hilbert space, this vector space V grows exponentially in D, right? Somehow if we say C2s at each factor, we have D of them, it's 2 to the D-dimensional space. In contrast, these marginals, say if we care about all the, say, 2 particle marginals, say, then only, this will only scale polynomial, right? Because there's only so many pairs of particles. So that would be, would be a great saving if this was not a very hard problem to do, right? And some of the reason why it's interesting is also somehow to prove why this is a hard problem. It's QMA hard, so it's like quantum NP hard. Yes?
Is this more general than the local Hamiltonian problem?
You can basically reduce, one to the other. Yeah, I think that's fair to say.
So it's QMA complete, essentially, is what you're saying, or is it because local Hamiltonian is QMA complete like the
That's a good question. Is it in QMA? I guess if you don't have this purity constraint, it should be in QMA. Matthias will know. Is it QMA complete if you don't have the rank 1 constraint? The, say, 2-body margin problem or the? We don't know, okay. Excuse me? No, don't require purity, just for mixed. Okay. Yes. And it's basically it's this reduction somehow energies you can compute using the 2 particle marginals.
Because you're projecting the tensor product on some specified local bound, and so you can construct any equivalent Hamiltonian that's local, the locality of projection.
That is basically indeed like what's going on here and behind this. That's correct, yeah. If you don't know what these terms mean, basically there's some of the fundamental problems that we want to solve in physics we could solve if we had a good handle on these margins. So now let's change gears a little bit and let's actually ask a simpler question, right, which is still interesting. Let's actually only look at the single particle marginals, right? So just as before, right, so we have, so basically in other words, we're asking, given just rho 1, rho 2 up to rho d, when are those compatible? And if I didn't care, if I didn't care whether this global state should be what I called a pure quantum state given by a single tensor, then this would be easy, just take the tensor product and you're good. But here we're interested in the fact, what if the global state is a pure state, okay? So in other words, we are exactly in the situation that we introduced 3 slides ago. X is a tensor. For a tensor, we can describe these marginals given by this flattenings, star, what we wrote down. And then we could ask, when are those guys compatible? And that's now sort of a highly non-trivial problem that somehow doesn't have really a classical analog on, because somehow what is a tensor here, so in the classical case, somehow corresponds to a deterministic probability distribution for which the margins are just deterministic. Here somehow, because of the presence of what we call entanglement, this is a richer space. And so in particular, let's even say if you have 2 quantum particles, they're basically in a single pure state. So it's in this case, it would be a tensor with 2 indices, a matrix. Then there's a non-trivial constraint, and the constraint says that rho 1 and rho 2 must have the same non-zero eigenvalues. And the idea is basically if you have such a quantum state of 2 particles, as we are saying, it's basically a matrix, and the singular values, somehow of star and m star m have the same non-zero eigenvalues. Is roughly the story. Okay.
This is for pure.
This is for pure states. So now I should have been more clear about this. Now we are back in the pure case. Some of what I said before is kind of what's the status of the general problem, right? It's hard. Now we're focusing on this case of pure states and no overlaps. Okay. But something that somehow for probability distribution seems trivial, and here it's sort of highly non-trivial, but it gives rise to interesting polytopes that we care about for many different reasons, and we could hope to find efficient algorithms, and kind of the algorithms we hear about, for example, by Raphael has an interpretation in this context. Okay. So let's go a bit further. Okay, so let's observe that if we have d particles, not necessarily 2, then again the answer to this compatibility questions, when are the rho i's compatible or not, depends only on the eigenvalues of the rho i's. And here's the proof. Well, if you take your global tensor x and you apply a tensor product of unitaries, you want to ud to your x, then what will happen to these marginals is exactly only that you'll be conjugated by, so the ith marginal will be conjugated by the ith unitary, so that's an operation that leaves the eigenvalues invariant. So that shows that in the end you only have to care about eigenvalues. And so the natural definition to take here now is we look at the following set delta. What do we do? Well, we look at all vectors of unit norm, so these were our good quantum states, our global quantum states. We compute, well, first these marginals, rho 1 to rho d, these quantum marginals, and then we diagonalize each of the quantum marginals. We get a probability distribution. Let's just order this distribution for concreteness. So let's call these bold letter p I x. Okay, that's it's a bit of a mouthful. So that's a vector. It's the vector of ordered eigenvalues of rho ix, and rho ix is the ith marginal of our quantum state x. Okay, so sadly we have to unpack this now. So that's, but given this definition, that's a simple object. We just look at all this, this collection of eigenvalues. So if you have d particles, that's like in each of dimension n, it's a d times n dimensional space, no exponent. So here's a simple example. If you have 3 tensor factors and all the local dimensions are 2, then because we have probability distributions, it suffices to just look at the largest eigenvalue of each of these 3 marginals. So we get a 3-dimensional space that looks like so, and it's some interesting polytope. Okay. And the amazing fact is that somehow the answer to this problem is always given by convex polytopes. So if you fix the dimensions, right, n1 up to nd, then somehow the set of compatible eigenvalues is always a convex body. And it's kind of highly surprising, right, because the set of unit vectors is not a convex object, nor is the map that diagonalizes matrices linear, right? Sort of both arguments fail that we had previously in the case of probability distributions. But still, somehow mysteriously, we get these convex bodies, and we could ask, what do they look like? Can we compute them, etc.? And so now we could go further, and we can also ask a scaling problem. So suppose we have some starting tensor y, we apply a scaling, which remember now means that we apply a tensor product of invertible operators, g1 to gd. We get some other quantum state x. Let's suppose it's normalized again to a unit vector. let's also allow ourselves to form limits, then we can define an object just like before. We vary over all the scalings of this fixed starting tensor y. We look at the marginal and look at their eigenvalues. Again, we get some convex, some body, and amazingly, it is again a convex polytope. For d equals 2, again, we understand what this means. It's basically just the only thing is that the rank cannot increase. The rank of the row i's cannot increase when you apply such a scaling. That's the analog of the support condition for probability distributions. But that's sort of the only analog, right? And so for d larger than 2, we get interesting gadgets. And so a while ago, we called these things entanglement polytopes because we related them to some entanglement properties of quantum states, okay? So these things will appear again. Matthias's talk here, 2 examples. The numbers in the flag mean that those are the non-zero entries of our tensor. So we put a 1 in the 0, 0, 0 component of our tensor and a 1 in the 1, 1, 1 component of our tensor. All the other values in the, say, 2 to the 3-dimensional, like this 2 by 2 by 2 grid are 0. That defines a tensor. Similarly here, we have a different non-zero pattern, different quantum state, in fact. And here would be 2 examples of such polytopes. Again, here we just get the same polytope as before. Somehow this looks generic, whereas if you take this tensor, you get a smaller polytope, okay? But again, it's not at all clear why these should be polytopes. So that's about the setup, okay? So are there any questions just about this definition? Because I realize this somewhere. Yeah. Yes. Could you say this again?
The W is the orbital of the Y.
Of the while?
We have these 2 tensors, W and Y. I just wanted to comment.
That's correct. That's correct. So the orbit closure of this guy is in fact dense. That's correct. It includes the W, and hence, as a consequence, one polytope sits in the other. That's correct. Yes. So that, and it's that is correct. Yeah. And it also points to like a remark, to an interesting fact that somehow, in the limit, this tensor rank can go up somehow, right? That is something maybe someone will comment on, but maybe I will not. But here it's true. Like so these are like marginal pictures, right? Pictures of the marginals. These are tensors in the vector space of tensors. So there's this group of scalings acting, right? And it is true that W is an asymptotic scaling of Y. And so it should better be true that this polytope is contained in that one, right? So that is exactly. That's exactly right. Thank you. Let's just maybe talk a bit about why you might care about such things. And basically, I mean, so there's a bunch of problems that we can put in those frameworks and from different directions. One is sort of, if you care about quantum information and entanglement, then that's the motivation we spoke about before. The tensors correspond to quantum states, pure quantum states. The scalings correspond to certain local transformations. The picture to have in mind is that you have your particles, you're allowed to manipulate them locally. There's sort of a communication model going on, as maybe you would call it sort of in computer science. So you're allowed to do local quantum operations, and you're allowed to send each other classical messages, and you're allowed to post-select on measurement outcomes. If these things don't mean to you, anything to you, don't worry. So that the idea is that there's sort of an operational interpretation of this group of scalings, right, that we care about. I guess in algebraic complexity theory, geometric complexity theory, tensors have a different meaning. They correspond more to computation problems. They could be the determinant or the permanent, for example. And the scalings amount more to reduction. So here it's like, in the first example, it's kind of like entanglement reductions. In the second is algebraic reductions in this context. We may or may not later see that there's a connection to invariant theory. And so, for example, the famous Kronecker coefficients appear in this scenario. The polytopes describe aspect of the asymptotic, so that's interesting for a different field. And then, if we looked at tuples of tensors, then a special case would be operator scaling with all these amazing applications that we already heard about yesterday. But okay, but what's the general mathematical structure, that allows us to get convex polytopes in such non-obvious situations? And again, it's related to the fact that there's a moment map floating around in the background. So Ankit explained that a map that takes a vector to its tuple of margins is a moment map. And so let's see what is true for general moment maps. And this will be sort of, another sort of unsatisfyingly general slide that we will again move away from soon. So here's the convexity theorem if the group is not abelian. And for concreteness, because we care about this for this quantum margin problem, let's suppose our group is just a product of GLNs. So here's GLN1 up to GLND. This pi is again a representation. And now we have again a moment map, the moment map mu, which then has D components, one for each GL. which takes a vector and now sends it to a d-tuple of Hermitian matrices. Again, the example to have in mind, sorry, I guess I wrote it here, is you take a tensor and you send it to its d-tuple of one single particle quantum marginals. As before, we want to normalize things. We want to basically make V norm 1. It means because the moment map is quadratic, it means normalize the moment map by the norm squared. So we now have, so that's the first thing we do. We take our vector, we compute the image under the moment map like so. We get a d-tuple of Hermitian matrices. But now we are not done. In the commutative case, we were done. But now we do a next thing. We diagonalize each of these matrices, and we replace each ni by ni matrix by a vector of length ni, which is just the eigenvalues, the ordered eigenvalues of this operator rho I, because it's Hermitian, that's a well-defined thing to do. So let's say bold P of V is this long vector of eigenvalues of these matrices rho I. So it's a space, it's a point in that space. And so now what we're interested in again is these two things that we can now define abstractly. So the first would be the set delta, which is just the set of all the possible local eigenvalues that we can get. That encodes the solution to our compatibility problem. And the second is the more refined problem. Suppose we start with some tensor W, some vector W. We apply arbitrary scalings, asymptotic scalings, because we take the closure and we look at the set of margins that we can obtain in this fashion. That's so this set delta of W encodes the solution to a scaling problem. Okay. And the remarkable theorem here that sort of goes, well, maybe in this special case, possibly goes back to Mumford, but certainly in generality was proved by Francis Kirwan, was that such objects are again convex polytopes by the nature of the setup. Okay, so this is this sort of second kind of convexity, so the sort of hidden convexity here that makes these objects moment polytopes, and we call them moment polytopes. Sometimes you may say non-abelian or non-commutative moment polytopes because the group GLN1 up to GLND is non-commutative. Okay, so that's the general convexity theorem. I may not discuss about the next example, but we heard this briefly. Oh, no, actually, this I will discuss about, sorry.
We'll have a bit more time because we have lots of questions. So.
Okay, great. Then maybe I can, thanks. So let's maybe, so this was sort of the general convexity result that we spoke about. So, you could now, this is also true for general groups, but let's not worry about it. So here we had these two extremes, right? We had an orbit closure, which is kind of the smallest thing to look at. We had the whole vector space, it's the largest thing to look at. In general, there's many interesting varieties in between. For example, there's things we call matrix product states or tensor networks. These are like nice, sort of efficiently describable classes of quantum states. We really care about how to calculate these polytopes for them. So that these kind of gadgets, these kind of situations exist also. Okay. But what's the point? The point is, well, we can again, summarize what we learned. So these marginal problems, these special marginal problems of pure quantum states that we cared about, we can interpret them in this much more general context of moment polytopes for non-abelian groups, for representations of non-abelian groups. But here, in contrast to this commutative case, the fact that these are polytopes is not at all obvious. And the theorem, unlike previously, does not give us an explicit description, right? So previously I just said it's the convex hull of all weights, or it's the convex hull of the support. Here somehow things are much richer, and it's related to what Ankit was saying, that somehow in the non-abelian case, you have to look at all bases at the same time. So kind of you have to sort of understand all the supports at the same time. And I mean, that's sort of heuristic reason why it's possibly more complicated. Okay. Nevertheless, there's explicit inequalities that people have derived, and I want to stress Nicolas Resser's results, because he gave a precise and sharp characterization of these polytopes. Sadly, this quickly becomes intractable. Intractable in quotes means sort of I don't know how to calculate them for sort of larger values of d and n. So even if we have 3 quantum particles and the local dimensions are 4, so 4 each, somehow there's lots of inequalities. I mean, this my extreme is not a lot, but the way these theorems work is they give you a huge class of candidate inequalities, each of which you can check efficiently, but to do all this work actually requires a lot of time. Okay. And one can show that in general, these polytopes have exponentially many facets. So they're not given explicitly, but if you do hard math, you find that they were exponentially facets in general. On the other hand, I told you that I can verify somewhat efficiently, if I do have a facet. I can also prove to you efficiently that I do have a point in the polytope, but just giving you a tensor. So that suggests that, that shows, and we proved a little while ago, that this allows you to put this membership problem on the polytopes in NP and co-NP. So we can witness efficiently, we can certify efficiently in sort of the appropriate sense that there is a point in the polytope and that there is not a point in the polytope. And so that's kind of interesting, right? So somehow this description in terms of just listing as fast is not efficient, but you might, just because of the fact that it's a membership problem, it's an NP and co-NP, we would believe that there should be different ways of representing the polytope, not by linear inequalities, which are efficient, and so it really does call for algorithmic explanations, and that's sort of like another interesting motivation for all the works that's been going on here. Oh yeah, good. Yeah, so this was in the cone setup. So that is up to permutations. There's some like here the dimensions are the same, so you can permute the 3 particles. There's sort of a discrete symmetry in these polytopes. If you forget about them, you could ask, is this number large because there's a high symmetry, or is it really large? So some of the smaller number is up to. That's right, yeah. Yes. That's correct, yeah. Just because all the 3 dimensions are the same in this equation, yes.
Do you have bound on the bit complexity of these methods? How do you get NP reflection points?
Yeah, so you need to work a little bit about truncations. You need to sort of worry about that the vaults of these polytopes are not too steep and so on. So you can obtain a lot of like structural results from these explicit descriptions by Nicolas and sort of some variants that I've worked on with Michel Vernier. But you can't use the theorems to compute the polytope, but they give you a lot of information. They kind of so basically indeed that in our paper with Peter, Matthias and Ketan, we kind of worried about this fact, right? We had to worry about truncating all these things, right, and making sure it still works. So that can be done. Yes. So. I mean, the setup is here, right? You should imagine the setup is more like someone, here it's about the general polytope, but you should imagine someone hands you this polynomial, not as a black box, but as a sum of monomials, right? So it's not the hard problem that unit solve, but it's sort of the problem that seems very simple, but in the non-commutative case, not at all simple. It's basically like, yeah. Yes.
So but they assume there's such inequalities that they can check them using semi-definite programming. If I want to check second plus, let's say I want to check some of certain eigenvalues, and eigenvalues are rational numbers. So how you do it? But in some cases you can do it by semi-definite programming.
I mean, so here, I mean. Right.
So if you produce a plane saying the point is not in the polytope and there is a description of the plane, then one has to prove that the description of this plane is small.
Yes, but say you want to prove.
So that's exactly the kind of things we know. Yeah.
Specific inequality is satisfied. How do you do it? So specific inequality involving eigenvalues.
So therefore, so the way we don't do it, the specific inequality, like oh, you mean like given the tensor, right? Right. I mean, so indeed, you have to worry about like truncating stuff and so on and so forth. That's right.
Probably what is happening is that you do via semi-definite programming.
No, we don't. But yeah, no, we. Yeah.
To check whether first eigenvalue.
I understand. Yeah. I mean, what is true though is like that you could produce all these inequalities by such variational kind of principles. That is true, and you get the complete set. We use sort of the outcome of such an analysis. So there's sort of a finite set of linear inequalities, but I mean, I agree. So there's like things like the I don't know, it's like this Courant minimax principle, like all these variational principles for eigenvalues. There's more sophisticated versions of this that allow you to target specific linear combinations of eigenvalues, and that certainly goes on behind the That is not what Nicolas does. That's not what we did, but it is one way of getting all these inequalities. And that may also lead to different strategies here. Yes. Let's maybe. I mean, I can tell you more about like what's the input size and all the specifications here. Maybe afterwards. This is a problem that maybe I should skip. It's an interesting problem that I think we already discussed on Monday. It's a non-marginal problem that still fits into this framework and sort of quite well known. It's the following problem. Suppose I have a triple of Hermitian matrices, and I want to ask, what are the possible eigenvalues of, this triple of matrices, so of A, B, and C, under the constraint that they sum, that the sum of A and B is equals to Z. So again, it's not clear. Like, it's easy to write down certain inequalities. For example, using such variation principles, you can easily see that the sum of the largest eigenvalues of A and B should be at least as large as the largest eigenvalue of C. All inequalities here are of this form. They are linear inequalities of the eigenvalues. So again, there's a convex polytope that's going on. It is described by a redundant set of inequalities conjectured by Horn. This was later proved by work of Klyatschko and finally Knudsen and Tau as a consequence of something called the saturation conjecture, which maybe I won't go into much here. And interestingly, this connection, right, has then been used by Ketan to show that actually the membership problem can be solved in polynomial time here. Okay, so given a triple of, say, rational spectra ABC, when does there exist ABC, that we know how to do. As far as I'm aware, in the general case, the case of general marginals, we don't have a polynomial time algorithm to find them, but we have interesting scaling algorithms by Cole-Franks that do so. I'll not tell you why. It's just a nice little exercise. Again, characterizing these eigenvalues amounts to characterizing a moment polytope. It's a moment polytope. Well, since we have 3 marginals, we should have 3 copies of the group GLN. It turns out, since we have 2 matrices here, A and B, we should have 2 matrices in the vector space that we care about. So indeed, the group is GLN3. The vector space is 2 copies of the n by n matrices. And there's a funny action that one can relate to this eigenvalue problem. Just as a comment, I mean, this, as we sort of learned previously, this term moment map, I mean, it comes from the momentum. So there's many further examples of this in say, classical mechanics. The connections this moment map makes sense. I mean, the definition of a moment map makes sense in more general context of symplectic geometry. Natural sources of symplectic manifolds are phase spaces in classical mechanics. So there's sort of a rich family there. Yeah, yes.
For this action,
yep.
for GLN3, the multiplicities will be little Richardson coefficients.
That's correct, yes.
Exactly.
Yes. Yes.
Just to make a connection to my thought.
That's correct. Yes. And again, some are, these are general matrices, but something like MM star will in particular be Hermitian, even positive. So there's a little shuffling, so maybe I shouldn't have written down the formula, but there's a way to do it. Good. So maybe, so if I get like 5 more minutes or so, then maybe I want to end just by, I mean, there were questions yesterday. How does this non-commutative duality that Avi alluded to, that Ankit described as this Kempf-Ness duality, how does all this generalize to now other points of the polytope, right? And so let me just recall what we were saying, right? So the point of all this enterprise was that we can scale to uniform marginals if and only if we're not in the null cone for a corresponding group action. So that was what Ankit explained. And we also learned in Harm's talk that the null cone is exactly cut out by invariant polynomials. So we have this equivalence of 3 statements that we can now phrase in our language, right? We said that zeros in the image of the moment map, of the moment polytope for some W. This just means that there exists a scaling, possibly an asymptotic scaling, that has uniform marginals, right? That was the sort of the entire connection from before. Now the second statement says sort of geometrically that we are not in the null cone. If we minimize the norm square over the entire orbit or orbit closure, we never get 0. And the third statement is this translation into the terms of invariant theory. It's the existence of an invariant polynomial that can separate our vector W from the all zeros vector. So in particular, if P is homogeneous and non-constant, then this is just a 0 point, right? So this is sort of Ankit's talk, and this Harm explained to us, I think. Now, indeed, I was saying uniform marginals correspond to this origin of the polytopes, so of the general moment polytopes, or here of these entanglement polytopes. So we may ask, what about other points in this polytope? Suppose that's your favorite point P. When is this in the polytope? In other words, when starting from a tensor W, can you scale by, say, this GLN group, this to another quantum state where the quantum marginals have eigenvalues P1, P2, P3, vectors of eigenvalues P1, P2, P3. And I'll only give you sort of a heuristic summary of the situation. I won't prove why this is true. But the heuristic idea is we're going to start our intuition from the right-hand side, right? So on the right-hand side is about the existence of an invariant polynomial. Now, an invariant polynomial is just a trivial representation. It spans, well, an invariant polynomial, if you look at the one-dimensional vector space spanned by it, it's a one-dimensional subspace of the polynomial ring, of this vector space of polynomials here. And it's trivial, right? Because invariant, it doesn't change on the group action. This just means it's a trivial representation that it generates. And now we learned from Peter's talk that, there's a sort of a nice way of characterizing arbitrary irreducible representations that are not necessarily trivial. And the way this went was this theory of highest weights. So there was, we could always look at the torus, diagonals, and so on. So the point is that in any representation, in any irreducible representation, say of GLN or of product of GLNs, there exists a canonical vector called the highest weight vector. In our case, it will be a polynomial because our representation is the space of polynomials that we care about. And it is uniquely specified by, well, it's not an invariant polynomial under the whole group, but it's a nice eigenvector of a subgroup, the subgroup of upper triangular matrices, what is sometimes called a Borel subgroup. So in other words, this polynomial is if the representation is irreducible, uniquely, specified by this property, defined by such a property, if we, instead of, this should be P lambda of V, if instead of plugging in V, we plug in, the element that we obtain by applying this group action with an upper triangular matrix B, then what pops out is, this will not give us exactly V back, but it will give us, P lambda of V back up to some scalar multiple, some eigenvalue, and this eigenvalue is given by this function that Peter explained called the character, okay? So you should think of lambda as a collection of integers, okay? And this object is, it's like if you have a diagonal matrix, the first entry to the lambda 1 times the second entry to the lambda 2. So it exactly looks, for diagonal matrices, it looks exactly like these representations, like how you act on monomials. But now somehow you allow yourself to act even by upper triangular matrices, and you still want to be an eigenvector, right? So this is a non-commutative group, but you still want to be an eigenvector. So again, I apologize, this should be P lambda of V, okay? So the polynomial transforms as an eigenvector of this group of upper triangular matrices. And now there's a theorem by Mumford that says that, okay, that's exactly the correct way of generalizing, right? So, and the intuition is, right, lambda equals 0 just means nothing happens at all. This will be the constant 1 function. So our polynomial is completely invariant. Now it has a more general covariance or equivariance property. And the exact, eigenvalues, so these joint eigenvalues are captured by these lambdas, and they exactly correspond to points in the polytope. More precisely, we have a following characterization that it looks a bit complicated. If you are interested in, say, this entanglement polytope or this moment polytope of an orbit closure through W, then what we should do is now we should look at general highest weight vectors, so polynomials of this form. And we should basically evaluate these highest weight vectors at our vector V. Let's ignore the G0 for a moment. And if it's non-zero, we get a point in the polytope. The point in the polytope we get is exactly this highest weight, which is an integer vector, divided by the degree in which this highest of the polynomial P lambda that we found. So I sort of apologize for the fact that this is slightly complicated statement. I think Raphael will in part build on this, so let's just walk through it slowly. So there's two complications. One is that there's this weird lambda star. This is just some reordering that we won't worry about. It's related to the fact that we use the inverse here, and that's neither Peter nor Harm explained. So I also won't go too much into detail. So the inverse translates into some minus signs. That's not so important. Essentially, we're looking at highest weight vectors corresponding points in the polytope. The other complication is that there's some group element G0 sitting here. So this statement will only be true if you first apply some like randomization, if you wish, a generic element in your group. So more concretely, you take your tensor, you take your vector W, you apply some random group element, and then you just check, is there a highest weight vector? Is there a polynomial that is simultaneously highest weight vector and non-zero on your point? Okay, and that will give you all the points in the polytope. And just to confirm, right, if lambda is a 0, then this could appear in any degree. It will always give us the 0 point in the polytope. So it means exactly if the 0 point corresponds to an arbitrary invariant polynomial. But sort of this now points to all the this gives you a characterization of all the rational points in the polytope. There should be a closure. So
this condition looks a bit complicated with the G0, but it just means that the P lambda star is the highest weight vector. When you restrict it to the orbit closure of W,
That's right. I mean, and somewhat conceptually, right, what it means is that this highest weight vector is only one vector in this irreducible representation. And you get a point in the polytope when somehow there exists any polynomial in this irreducible representation that is non-zero. Right? So somehow because these irreducible representations, if you don't have invariants, are higher than one dimension in general, that is exactly where this G0 is coming from. So we have to make our life a little bit more complicated.
So this means in the coordinate ring of the orbital coordinate of W, the highest weight lambda star appears. I mean, the irreducible representation.
That is correct. Yes. 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 That's correct. And in fact, let's just, because it's a bit of a complicated statement, let's restrict to the case when we don't fix W. So we don't care about the scaling problem, but just about the compatibility problem. Then one can write down something easier, right? It's the following statement. Let's just first look at this line. So this whole polytope is just exactly given in this way. So you take your degree k polynomials, you decompose them into irreducibles, which we know we can always do. And if there exists an irreducible representation of type where the prime number is lambda of type lambda, or its dual in this space of polynomials, then we get a point in the polytope. And if we look at all the degrees, we increase k. K is arbitrary here. We get all the rational points in the polytope. In other words, here's a more sort of quantitative, a way of relating it to things that people like to study. Let's define m sub k of lambda as the multiplicity of an irreducible representation, labeled by lambda, in the degree k homogeneous polynomials. What I'm saying is that if this multiplicity is larger than 0, we get a point in the polytope, and all points in the polytope that are rational are obtained in this way. So it's exactly this statement over here. And the reason why I'm telling you this is because these are really interesting numbers. So for example, for this tensor scaling setup for the margin problem, these are exactly the Kronecker coefficients, which one can also define using the symmetric group. In the case of this Horn's problem that we just briefly looked at, you get exactly the Littlewood-Richardson coefficients. And so the picture you should have in mind is kind of the following. So this is here, you see on the bottom of this picture, you see a two-dimensional polytope. There's some weird shape over it that you may ask me later what it means. Now, each point on the polytope I explained to you should correspond to some non-vanishing multiplicity. So let's just decompose the degree k polynomials for larger and larger k into irreducibles. Let's look at this multiplicity function. So we get like a point cloud over this two-dimensional space. So this would be like lambda 1, lambda 2, and the multiplicity is the z-axis. And so we see that this becomes a smoother and smoother continuous shape, and the support of this function is exactly the moment polytope. It's this black shape, and there's even some more refined information that we don't talk about. Good. So I should wrap up very quickly. Let me just say that there's interesting problems here, right? There's the counting problem. What is the multiplicity? There's a positivity problem, and we can ask what is the moment polytope problem? And the moment polytope problem is basically exactly can we, given a point p, does there exist some lambda and k, not necessarily the smallest fraction, right? But you could multiply everything by s, so that this polytope is non-zero. And there's an interesting difference in complexities here that, again, I will not go into. Someone asked about yesterday, but I won't tell you. So there's a way of generalizing this optimization duality to arbitrary points in the moment map. We can talk about this during lunch. So let me just summarize very briefly. So the point, right, was where we discussed three things. We discussed, the convexity properties that are really sort of at the heart of these optimization algorithms. It's the convexity property of this norm square function as we move along in orbit. Then we explained that the gradient, this moment map, is not only interesting if you like to minimize the norm, but it's sort of related to natural marginal and scaling problems, which of course we have already seen in a previous talk. Both problems relate to probability distributions for commutative groups and for quantum states for non-commutative groups. And these polytopes, right, is sort of like this, surprisingly, there's polytopes that encode answers to these problems. They have these dual descriptions that we will meet again. And the interesting thing is really, right, these are complicated objects. We can't naively write them down, just in terms of facets or so. Yet there's all these beautiful algorithms that we are discussing this week that are sort of connected to them. So that's, I guess, concludes my tutorial. Thanks very much.